So, good morning and welcome back to Advanced Image Synthesis. And today we'll continue with compression and, address more specifically what we actually wanted to get at, and that is image compression. So, last time I stopped here with a brief overview over PNG, the Portable Network Graphics Standard, which in a sense supersedes the GIF standard, graphics interchange format. But as I mentioned already, there's this somewhat strange design decision to split up animated and non-animated graphics. GIFs are still around, even though it's clearly the inferior format, but somehow the animated version of PNG, which is called MNG, Multiple Network Graphics, never really caught on traction. So we're still stuck with those silly 256 color animated images. But nonetheless, what was the plans in the development of PNG? One of the big things is the patent issue that I mentioned the last time, or was the patent issue. The patent has expired now, but since the compression scheme, the compression algorithm that was used in GIFs was under patent, the entire format wasn't really open. And as I already mentioned, there were actually legal actions taken against some software packages that didn't pay patent royalties. I think GIMP was a particular example of that issue. So, but that isn't all. PNG also has a lot of other things that it supports. For instance, it supports 8-bit palettes, sure, just like GIF. But on top of that, it can also do full n bits, n being 1, 2, 4, 8, or 16 bits per channel color. Okay, and that includes alpha. So you can also do 1 or 16-bit alpha, whereas in GIF you only have one transparent color. So that gives you a lot more flexibility. And in particular, the big deal is n bits per channel over just paletted colors. So you can finally use more than 256 colors, which is kind of usual these days. It took a while for this to be supported by browsers. Why do I mention browsers and not graphics programs? Well, as I said, PNG and before that, GIF were standards that were developed with the internet in mind. So when they were developed, in particular PNG, internet was growing and growing and became the thing that we know today. So it was kind of a big deal for a graphics format, whether it's supported in a browser or not. And it took surprisingly long for some browser to support it. Most notably Internet Explorer, which doesn't even exist these days anymore. I think Microsoft still supports it, the latest release, but they've released Edge for a while now. I'm not even sure if they still support Internet Explorer. Well, nonetheless, in the good old days, or in some intermediate time interval, Internet Explorer was really the #1 browser by a large margin, and that didn't support PNG, which was a big deal. Again, no support for animation because there was this other MNG format on top of that to separate things out a little bit, but apparently no one ever thought about this. So one thing I left out in this list here, the second one is, and that's kind of the important thing, and that's what I want to talk about now. How does the compression in PNG work? So it's pretty much a 3-step process. I already talked about LV77. Remember, that was this triple encoding where we have this look ahead and this a sliding window approach, and we encode sequences as 3 things: a starting point in the sliding window, then a sequence of characters or elements, don't necessarily have to be characters, but a sequence of code book entries or code entries, and then the next entry after that. So the issue with that one is that it might blow up data significantly. So remember when there was a letter that we haven't seen before, we encode it as 00, that letter, and if we're unlucky, we end up with a lot of these 00 something sequences. And in general, there's a high likelihood that these numbers, the first two numbers, appear fairly often in the data stream, so unusually often. And that's what Huffman coding is used for. Huffman coding, again, remember, that assigns a variable bit length to various symbols. So symbols that occur very often get a relatively short bit sequence assigned, whereas symbols that appear rarely get a longer one. In essence, the hope is to achieve with this adaptive coding to achieve an overall shorter bit sequence of the entire data. Okay, so and here it makes particular sense since we create these triples, whereas the first two things are numbers that occur unusually often, are usually relatively small numbers that occur unusually often. So that's the basic idea, but there's one more thing on top of that, and that's the pre-filter. And that is very specific to images, while the second two, LZ77 and Huffman coding, are nothing that are special to images. And as a matter of fact, that's pretty much deflate, which is what we use in zip. So let's look at this pre-filter thing. What is this really about? And the idea is, and that's generally an idea in data compression and in particular image compression, the idea is to reduce just the size of numbers. Okay, so if we have a sequence with numbers, say from 1 to 100 or so, just generally without a loss of information through some process, reducing just the magnitude of the numbers. If those are integers, we also reduce the numbers that are used, right? If I use numbers from 1 to 100 and I reduce them from 1 to 10, that means that in total I have a smaller alphabet. I only use 10 different characters, which then make the rest of the encoding process easier. So LZ77 will have a higher likelihood of finding sequences if there aren't so many characters around. And also Huffman will benefit from that if there's, fewer letters in our alphabet. So how do we achieve that in PNG? And the idea in PNG is that you often have either long uniform sequences of numbers, that's cool already for LZ77, or you have gradients in your image. So it's fairly often the case that you have a linear gradient in your image. So something changes from, I don't know, red to green, for instance, in this image, or white to black, or at least you have, instead of just a step black to white, you have some sort of transition region. So that happens pretty often. And the idea is to capture this or to use this by technically computing a sort of a gradient. Compute a gradient of a gradient. Yes, one is an image gradient and the other one is the mathematical derivative gradient type of thing. So what we do in PNG images for every scan line, so this can alternate or change in every scan line. There's basically 5 different modes that we can choose from. The first one is do nothing. Okay, so that's easy. The second one is subtract, then up, average, and the final one is the path predictor. Let's first look at mode 1, 2, 3. So what these modes do is they compute the sub is the difference to the left pixel. So just the subtraction from the left pixel. And that's really the derivative, right? Or it's the difference quotient to be precise. So it's an approximation of the derivative. And the idea is if I have a linear gradient, then the derivative is a constant, right? So the difference to the previous pixel is most likely to be smaller than the pixel values themselves. Remember, we're trying to crunch things together to make them smaller. And in the PNG case, without a loss of data. And when we look at JPEG in a few minutes, we'll see that we are also willing, in some cases, to accept the loss of data just to make things smaller. Okay, so the difference between two values is likely to be way smaller than the values themselves. Okay, in particular for a gradient situation, this is going to be a small number. For a, which is technically also a gradient for a uniform for uniform values, if you have all, I don't know, all reds, if you compute the difference, well, this will all be 0, so perfect. Okay, and you now might have a gradient in x direction or in y direction, and this is what sub and up are good for. So sub is the difference in x direction, and up is simply the difference to the previous line. And the next one is the average. So in this case, you use the left and the upper value and compute the average of the two, which is kind of the same, but just taking both of these values into account. Notice that we never look at the right or the bottom value. The reason is very simple. We save the image scan line by scan line. So when we later want to recover the data, we don't have the right or the bottom value available yet. So we can only, if we want to regenerate the original data, so from the subtraction, again, generate the original values, we start with the first value, which is encoded as it is, and then we simply store the deltas to the previous one, and that of course means we can't use something that we haven't looked at yet. Okay, so those are these two, and then the path predictor is kind of the sort of gradient type on speed. So here's the path predictor, and it takes a while to kind of get into this idea. So it's been developed by a person called Alan Path, so that's where the name comes from. And the idea is really to take the left difference, to take the upper left difference, and to take the above difference. So look at all the three values around at the current point, and then pick from the three the minimum distance and store that one. Okay, and do that in a specific order. So if the differences are equal, we pick them in a specific order so that we can in the decoding step determine which one we picked in the encoding step. Path is usually superior to all the others, so except if you want to have a simple computation and you have a perfectly horizontal vertical gradient. So while it is technically possible for each line to choose the one, the mode, whether none, sub, up, or so on, or path, separately to pick the one that is best, in practice today, pretty much every line is encoded by path. Okay, so that's one of those things, again, that were designed in the standard that were kind of a nice idea, but then in practice don't really make a big difference to choose anything else. So that's pretty much what every line gets crunched down to. So we're, in a sense, computing that derivative thing in an attempt to reduce the numbers closer to zero, or closer to uniformity. Then we run LD77 on top of that, run Huffman coding on top of that, store it, add a little bit of additional data. So there's of course some header associated with the file that stores width and height and the parameters, what's the pixel depth is, length. There's a bunch of nasty things that need to be done on top of what I explained here, but that's pretty much what PNG does. Okay. Key observation here, it's lossless, so it's not going to compress as well as a lossy format most likely, but it preserves the original data, and it's particularly useful for situations where we have large uniform areas or where we have gradients. So those are kind of the things that we handle particularly well, and in practice, that is something PNG is useful for things like for instance, if you have cartoon style images, right? So those are usually uniform regions with very sharp transitions, right? If you have your cartoon character, it's maybe, I don't know, yellow on a white background with a black border. That compresses much with much higher quality than with the lossless formats, or the lossless format that I'm going to present in a second, which is JPEG. Okay, so it's good for drawings, it's good for cartoons, these kind of things, but it doesn't compress as well. Okay, so that's PNG. Now, the other important format that I want to talk about today is JPEG. So how does JPEG work? What is JPEG? Well, it's a format that has been developed by a large group of folks called the Joint Photographic Experts Group. So those are people that apparently know how photographs work. They are from various industries like camera manufacturers, hardware manufacturers, software, all kinds of technicians, researchers that know what they're doing when it comes to photography. And photography is really the big deal. So JPEG is for photographs, which are different from cartoons, right? So they are very different in nature. It's a lossy compression scheme. Technically, it can do lossless. Well, not just technically, practically, you can set JPEG into lossless mode. But as I mentioned before, it's usually not worthwhile. So you want to use PNG instead of JPEG if you want to run it in a lossless mode. What was a really crucial design decision from the beginning on, it should be extremely fast, so it should be a very simple format, or a relatively simple format, should be very fast, and in particular, should be fast in decoding. So you want to quickly view things either on a camera or on, I don't know, well, some playback device. Okay, and it should be simple to be integrated into hardware. In particular, when JPEG was developed, software implementations and computers weren't as powerful as they are today. So it was thought of in the beginning that we want some specific silicon, some special silicon for JPEG decoding. And even to this day, that is present. I mean, software implementation of JPEG can be extremely fast these days with fast computers, but it's still worth to go through some hardware. And JPEG hardware is immensely cheap, and it's in pretty much any piece of device. And in particular, if you think about motion pictures, movies, also JPEG or variant thereof is used to encode certain frames in a video so that those can also be stored as separate images. And again, you want extremely fast decoding for images in a movie stream. So it works pretty much for all types of images. There's no restriction on color depth or how you want to store your colors. So again, that was a big deal compared to the GIF form. So here's kind of the overall idea. So that's kind of JPEG in a nutshell. So on the left, you see a pipeline view, and the right basically describes how the format conceptually works. So there are these steps involved here. First, you do a color space separation, and I'll go through all these steps in more detail in a few seconds. So first, you change the color space. If it isn't encoded in YUV or YUV already, you encode it in YUV. What that is, again, in a second. If you've attended computer graphics, you've heard the term YUV before. Then the data is processed block by block. You do DCT, discrete cosine transform. That thing is quantized. And finally, it's serialized. So it's written to a file and encoded. So let's go through these steps one by one. So first of all, I said the color space is transformed from, say, RGB or CMYK or whatever, HSL, or whatever is being used, to YUV, which is pronounced YUV. So what is YUV really? YUV is a format, again, I mentioned that in computer graphics in more detail. So if you're interested in color formats, you might want to review the color stream in computer graphics. But the basic idea of YUV is to separate the brightness or luminance information from the rest, called the chrominance information. Okay, so, and it doesn't matter that much technically how you do this. So there's different ways. For instance, I could encode color as RGB, right? Red, green, and blue, with all the advantages and drawbacks of that format. Again, more on that in the color stream. But what I could do is I could just simply say, okay, well, I can compute the brightness from red, green, and blue. Right? It's almost like the sum of the three. It's usually a weighted sum because we perceive blue a little bit darker than red and green. So it's some factor red plus green plus blue. And as a matter of fact, I've got these factors here. So it's 0.3 times red, 0.6 times green, 0.1 times blue. So you see blue is significantly downweighted and red a little bit over green. So that's really the brightness. Okay, and now I could simply store red and green. Okay, so if you look at that equation here, right, I store brightness as this sum here, and then I store red and green. I can, of course, solve this for blue, right? I can always recover the third component by simply inserting red and green and then dividing by 0. And subtracting that and then dividing by 0.11, and I get blue. So it's clear that I can just store two color components as well as the luminance on top of that. However, that's not what is done here. So luminance is stored kind of as is, but color is stored as this seemingly weird thing the change from yellow to blue and the change from green to red. Again, you can do the math, and I did it here for you, to compute U from RGB and V as well, and then again, recover from YUV, recover RGB. So that's the inverse computation. As you can see, it's pretty simple. What's the reason for that? And again, explain that in computer graphics as well. So if you use these kind of gradients instead of green and blue or red and green directly, you end up with smaller values. Generally, you end up with smaller values than just storing red and green directly. And the reason for that back in the days was to save energy in analog TV transmission station. And here it's kind of similar. We save energy, but not necessarily as watts, but as size in numbers. Again, size in numbers matters when we want to compress data later on. Okay, so this is what we do first, and this is lossless. Okay, so this is just simply a transformation, and if you do these calculations properly, notice that we start with integers, we do a floating point computation, and we end up with integers, so there's a rounding step involved. However, if you do this smart and you observe certain rules when doing rounding or ceiling floor computation here and here, you can make this work within the original data range. So if you throw in, say, 8-bit data values here, do your computation, then round it again to 8 bits, and throw in those rounded values here, do a floating point computation, and again round it back to 8-bit, you get exactly the same value. Okay, so that's guaranteed, and you end up with no loss at all. Okay, so what we just do is we do some color space transformation. That's step one. So far, the standard is lossless. Now let's lose a little bit of data. And also, why did we do this here to start with? Well, one idea was to reduce the range, or not necessarily the range, but reduce the kind of usual numbers. The range is the same, but the numbers are for normal images, for normal photographs, are now non-uniformly distributed. Again, just for, of course, you can generate an input image that will create an arbitrary output image. But we're again dealing with photographs. We're not dealing with special crafted noise here or anything. So the next step that actually causes some loss and starts to compress things is the subsampling step. It's a pretty trivial thing. So the idea is here to simply drop parts of the data to, for instance, drop every second number. And we do this in a selective way. So for instance, we can disable this drop. Or we can selectively drop some components. If we disable this, which is called full equality mode or 444, that would mean, well, we have no compression going on here and no loss going on. But what we can do is we can selectively drop data. And when I say selectively, I mean we drop data in the color channel. And that's the whole point of this color grayscale or luminance chrominance separation. The idea is that humans are not able to perceive color changes as good as brightness changes. As good as means spatially. So if we have two brightness values nearby, we can distinguish them pretty well. However, if we have two color values nearby with the same brightness level, we have a much harder time distinguishing those. Okay, so our color resolution is lower than our brightness resolution. And this here accounts for that, so that we can say, okay, well, we store the brightness, we store the luminance information at full resolution. That's what you see in the top, that's the checkerboard pattern. But that for the color information, we simply take just every second pixel in X or in Y, or we just take every fourth pixel. Okay, and the way this is, and you can basically choose from some of these subsampling schemes. 444 is the highest resolution. It's on the right. That means that color as well as chrominance, chrominance or luminance, color as well as brightness, is encoded just the same. Now, I personally find that very awkward. So this numbering scheme, so I always have problems remember the basic idea or understanding why it was chosen this way. So what do these four numbers stand for? They're kind of weird in my opinion. But anyways, so the first one stands for the basic kind of ground truth. Okay, so we can choose this any way we want, but it's usually chosen as 4. Okay, we could also say, I don't know, 26, but let's say we just fixed the first number to 4. It's kind of awkward anyhow. So let's say the first number is a 4, and then the second and third number just tell us how many chromatin samples we have in the first row. Okay, so what that means is, like, if you choose that as 1, for instance, right, as you can see here, we end up with 1 chromatin sample in the first row, and then B tells us how many additional chromatin samples we have in the second row. Okay, so let's look at this example here. So those are 8 values, right? So 4, 1, 1 means, okay, well, I've got 1 single sample for 4. So I have a downsampling factor by 4 to 1. That kind of makes sense, right? I mean, I get that part. So that this here is the downsampling in X. But then the second one is not the downsampling in Y, it's just how many additional do we have. So for instance, 4, 1, 1 means downsampled by 4 in X and not at all in Y. Okay, so this here is, so the ratio between the two here is kind of the downsampling ratio from X to Y. So this is how you can read this: downsampling from ground truth, or downsampling in X and downsampling in Y. Okay, so but 4 to 0, for instance, here the ratio idea doesn't really work because 2 divided by 0 is not defined, but it basically means downsample by 2, so that's fine. All right, and then use no additional samples, which means, well, just also just downsample that to just 1 pixel in X direction. Okay, so sorry, in Y direction. Okay, so there's just 1 pixel used in Y direction. So again, it's kind of awkward, and I never really understood why to do it this weird way, but that's the way it is. Okay, so long story short is, the smaller these numbers are, the second and third, the more you downsample. Okay, so 444 being kind of perfect, and well, I guess what would the minimum version be? I guess 410, I suppose, if I didn't make a mistake here, would be kind of the minimum quality. Notice that default is 422. Okay, so it's kind of default to downsample in X by 2 and not downsample in Y. Okay, so that's pretty much the downsampling step. And again, as I mentioned before, this is physiologically or psychologically kind of both motivated. So our visual system just doesn't see, or we don't see color that well. Okay, so let's look at a quick example here of JPEG images. So notice that I put 2 lines up here. So what you can see at the top are 2 images in 444 and 422 in what's called best quality. At least by some approaches, it's called best quality, and we'll get to this quality thing later on. But first notice that, well, this is original and this here is downsampled. It's probably pretty hard to see a big difference. I mean, if you look closely, you'll notice some difference, but that's the whole point, right? I mean, we're trying to lose data, which means the stream shrinks in size. That's not too noticeable. Notice that this here, those are images that are particularly bad for JPEG. So they are really, really bad examples. So those are images that you shouldn't encode in JPEG because they demonstrate very well what's going wrong. Those are obviously not photographs. I mean, they could be of a chart, but yeah, that's kind of silly to say, well, that's a photograph of a chart. It's not a chart. Okay, so long story short, that you don't see this very much. So if we add loss along the way somewhere else, it probably becomes a little bit more obvious. But again, you shouldn't look at the comparison of this one to that one, like full quality to crappy quality, super small images to significantly bigger images. But what I'm trying to get at is here is the subsampling step, right? If you compare this one to that one, yes, this one looks even worse, but still, this subsampling, this chroma subsampling actually works pretty well because again, it's motivated by the way that we see. And for real applications, for photographs, that's even less visible. Okay, so that was the first step. Now let's look at the next step, which is the DCT. It's a discrete cosine transform. And DCT is kind of the little sibling of the Fourier transform. Notice Fourier transform transforms a spatial signal into a frequency signal, and it's based on sine and cosine. So if you know a little bit about Fourier, if not, you might want to read about Fourier transform, but it's a transformation that is based on well, sines and cosines. What we can do is we can drop the sine part and just do a cosine transformation. And that's kind of the next step. To perform this, DCT prefers number between -1 and 1. So we'll first shift values between -1 and 1 with some quantization. For instance, if it's 8-bit, we transform data from 0 to 55, which is just 8-bit range, to -128 and 127. So we'll basically just consider the number signed numbers, that's it. And then again, we block data. I said we do blocking. We now perform the following steps only on 8x8 blocks, 64 values of data, basically a chessboard, and then encode all of those blocks entirely independently. Okay. The reason for that is again, it speeds things up. We do computations just with small blocks of data, they nicely fit in cache. And we're talking about cache, which is a piece of hardware. This is to make JPEG work on cheap hardware, because we have a very limited amount of memory that we need to perform these computations. You just perform this on one brick or block, and then write this out to wherever, like your disk or some global memory, and then you process the next one. So you have a very small working set. Very useful for hardware implementations, and a lot of things, since you have a limited size, can be implemented instead of loops. You can unroll all of those loops and implement that with actual silicon. So here's the DCT. So that's the formula of the one-dimensional DCT. And again, compare it to the Fourier transform. When, if you like to, you see that a few factors have been dropped. It looks somewhat complicated. It looks even worse if you look at the two-dimensional DCT, which is really just the one-dimensional tensor product. It's a tensor product of two one-dimensional DCTs. But I don't really care much about about this actual formula here. It's not as complicated really as it seems. I mean, it only involves cosine. It's cosine transformation. It only involves cosine and square root. So it's not completely off the chart. But nonetheless, we don't even need to worry about this so much. The only thing you need to understand is that the DCT, just like the Fourier transform, transforms a signal from its spatial form into the frequency characteristics. Like what are the cosines that I can use to make the original signal? That's kind of what it does. And when you want to depict that in 2D, the transformed signal, remember we are dealing with 8x8 blocks, so it's just 64 values. The transformed signal kind of lives in this space here. So this is the base. This is the base, really, or those are the base elements of the transform space. So instead of having 64 brightness values, we perform this computation on y, u, and v separately, so it's all scalar. Okay, so instead of having 64 different brightness values, we now have 64 values that are, well, low frequency to high frequency. Okay, and this is varying in x and varying in y, and then we have the whole tensor product. Okay, so on the top left, you have the lowest possible frequency, which is just uniform. Okay, and then you have one wave, you have 2, 3, and so on and so forth. No, it's not 2, 3, it's 2, 4, and so on and so forth. Okay, so those are just the number of oscillations kind of in x and in y, and then again, we have the summary, which ultimately gives us here one oscillation per x and y pixel, which is really a checkerboard. Okay. So what this transformation does, it takes the original brightness distribution and transforms it or takes it apart into its frequency components. Okay, here's an example of that. So if that is on the left is some random 8x8 brightness distribution, here also shown as a height field, then the DCT value, that's the DCT. So when you look at the DCT value, what you can see is that the numbers here are significantly smaller. As a matter of fact, pretty much everything is 0. right? On the left, you have a ton of crazy numbers, okay? And on the right, I have a few numbers and pretty much all zeros, okay? And this, again, is a lossless process. So I can take this here, transform it to the cosine space, and then transform it back. And again, you have to be a little bit careful here. The computations involve floating points, or you can implement them using floating points, and you need to round in the end. However, if you again do this rounding in a clever manner, and you make sure that when you throw away an error on one side, you recover that error on the other side, you can do a DCT and an inverse DCT. So basically taking these values, convert them to frequency space, then round them, convert them back, and you get exactly the same values back without any loss whatsoever. Okay, but still, what you get is, well, a ton more zeros, at least for that particular piece of data here. Of course, I can again construct a data set where this here would contain, that's probably hard for this one to contain, well, not a problem. Anyways, I can construct a data set on the left that contains relatively uniform data, but looks chaotic here. So sure, that's possible, but it's unusual for a photograph. Why? Because a photograph has smoothness in it. So if you take a picture of something with significant resolution or sufficient resolution, you'll always have kind of smooth areas. You'll always have uniform areas. And that's the same basic idea as with this pre-filter in PNG, where we try to smooth things out without losing data, not smoothing in a filtering, down filtering, high pass, low pass filter sense, but in a sense that we convert the data to a space where it's usually for the intended purpose, relatively smooth. Okay, and that's what we get here. So despite the fact that this is exactly the same piece of information, just in a different space, you see a ton more zeros. Okay, cool. Now let's look at that in action. Let's see what a DCT signal would create after an inverse DCT, after we transform this back. So just as a little experiment here, so if we would take a DCT and we throw in one value just in the upper left, what we get is, well, we get a uniform piece of data, which is no surprise because that's where the DC part is, the direct current, the plateau. And here it's visualized as a plateau. Now, if I add one more value, for instance, directly to the right, you see, well, an oscillation in X. So I can create a gradient here with just two numbers. Okay. So if I want more oscillation, I could just shift that, and then I would get kind of this, well, cosine-shaped curve here. And now I can add a few more numbers. So for instance, if I throw in one here, I get this overlapping situation of a gradient with this one oscillation. If I just copy the number to the bottom right, you see I get this checkerboard pattern situation here. And I could just throw in a few numbers in the top left and then create something like this here. So the thing that is noticeable here is whenever I throw data numbers, non-zero entries in the top left near the low frequencies, well, not surprisingly, I get a pretty smooth signal out, whereas I get, more noisy signal, more quickly changing signal pattern when I do this, when I add data to the bottom right. So assuming that our input data has some smoothness to it, we'll probably end up with just a few values. And the inverse is, say, so far again, we haven't lost any data. Now let's say, okay, we're willing to lose a little bit of data here. Where would we want to lose the information? Well, if we do the DCT and we end up with all zeros, it's fine. If we end up with a few numbers that are non-zero, but relatively small, okay, we can probably drop them without too much loss. And if we drop them more towards the bottom right of this DCT space here, or not just lose numbers that are closer to zero, but maybe drop the difference between 10 and 11, okay, or 28 and 29. So maybe just store even numbers down here and with more precision to the top left. Then we end up losing precision in the high frequency. And that might actually be useful because high frequencies could actually be noise. So So we might actually even improve the image technically by this process, always assuming that we're dealing with photographs. Okay, so and this is realized in JPEG by a method that's called quantization matrix. So what we do is we take this output of the DCT, which is just a matrix, right? I mean, let me just go one slide back. So the input is a matrix, right? It's just 8 by 8 values. The output is also 8 by 8 values. So I just call this a matrix here. Okay, so now we take this DCT matrix here and we divide it by something that we call Q. Okay, and that's something that we've previously agreed on. Technically, it's part of the file, so we can actually pick any Q, which is also an 8 by 8 matrix, and just store that as part of our file that we transmit. So what we do is we divide this DCT by Q. Now what this does is, assuming that Q has values that are larger than 1, they shouldn't be 0. It's probably a dumb idea to divide by 0. But if we divide by something that's bigger than 1, we'll reduce the numbers here, right? So notice that this division here is done component by component. So you take both matrices and we just divide the first element by the first, the second by the second, third by the third. So if we just put in something here bigger than 1, we'll get smaller numbers. Well, that per se doesn't really get me much, right? For instance, if I divide by 2 and I start with, I don't know, 3, I get 0.5, which is smaller, but it still contains the same amount of information, of course, because I could multiply later on by Q, and then I would, of course, get the original result back mathematically. Now, here is where data is lost, because we do a round step after that one. So what we do is we take our DCT matrix, divide it, and then round it. So basically kind of chop off, round, right? It's not chopping off the decimal point entirely, but it kind of adds things up starting 0.5 and then chops it off smaller than 0.5, right? You know what rounding is. So, and what this means is whenever we choose a DCT, a Q value bigger than 1, we lose precision after this process here, okay? So what we can do after that is we can take our reduced DCT and multiply it by Q. And if all the Q's would be 1, this would be lossless. I mean, which shows you what Q you need to choose if you want to run JPEG in lossless mode. But say if Q is if Q is 2, or if an entry is Q is 2, then this process here would basically kill every odd number, right? It would turn every odd number into its next even number. Okay, so that said, into the next bigger in this case. So that said, I can use this Q to selectively reduce the size of values and reduce the precision of values, creating a higher probability of nearby values being exactly the same, which is useful for compression. So here's an example. If that's, for instance, my Q matrix, notice that there's relatively small values in the top left and relatively large values at the bottom right. Not entirely, right? Notice there's some values here, like this one, suddenly smaller than the other ones around that. So how do I come up with this Q? I didn't come up with this Q. It's actually part of the standard, that particular Q. And again, that's psychologically, physiologically motivated. If you use a program such as GIMP, you can actually type that in yourself. So I don't think you can do it in the commercial product. I mean, I'm not an expert in Photoshop, but as far as I know, you can't. But in GIMP, you can actually do this. It's open source image manipulation program. You can literally say, okay, I want to store this as JPEG, and this should be my Q, and you get an 8 by 8 grid where you type in numbers. Okay, so if you want to, go ahead. I mean, GIMP is free. Download it, try it out. It works. And that is something that you can choose. The higher you make these numbers, the more your data will be well crunched on, the more it will be quantized. Okay, so, and the smaller numbers are, again, the better they compress. But the higher you choose these numbers, the more you lose, right? So if you choose, for instance, say you have values, let's just pretend we have values between 0 and 100. If we choose a number in Q like 50, all we get at output is either 0 or 1. So we'll basically end up quantizing our original data down to just 2 steps. But maybe that's going to work out fine already. So let's just quickly review what comes after that. So again, Q is part of the file. So we need to store that along with the file, or we need to use a Q that is part of the JPEG standard. So the last thing we need to do is our final compression. Now that we've got everything crunched down to 0, let's compress it. So first quick note, we traverse the data in what's called a dovetailing manner. So instead of just traversing the 8x8 block line by line, we traverse it diagonally so that we move from lower to higher frequencies. Okay, so that's the first thing to notice. And then we use sort of a similar idea to LZ and LZ77 and Huffman encoding, but it's all based on a fixed table. So it's not a Huffman encoding, it's then called entropy coding, and Huffman encoding is an entropy coder. So the idea here is that we have a fixed table of values. So our Huffman tree, in a sense, is predetermined, and here's what it looks like. So we say, well, 1 shows up pretty often, then the value is 3. From -1 and 1 show up pretty often, the values from -3 to 3 show up more rarely, and then so on and so forth. So this is simply sorted by size. So we expect small values to show up fairly often, and well, that's how we designed the whole process. Notice that the 0 is absent here, which is kind of awkward, right? Assuming that 0 shows up most often. Okay, so that's kind of like our Huffman table, or at least conceptually, that's like the Huffman table. So let's now see how the final compression works, and how do we get the zeros back. So we start. Again, we traverse this data kind of in this diagonal manner. So we start from the top left, and that's the DC component, and that gets encoded by 2 values. Okay, so the first one is the value which run length we pick. That is basically which entry here in this table, and then the second one is where in the table which value of that table. So that means that if we pick 1, we only need 1 additional bit to decide whether -1 or 1 is the right one. If we pick 2, I mean, we can't pick this freely, right? For instance, 15, we have to look up where's 15. 15 is here. 15 is in the 4th entry, and then we need, well, 4 bits. So this is why this is also called run length or size. Okay, so this tells us, the entry in the table tells us also how many bits we need to figure out which one is the right. Okay, so which one is the correct one. So we basically say, okay, 4th entry, and then 15, which is basically 111. Okay, so I've just spelled this out here as 15, and somewhat went wrong with my formatting here. So that's the DC component. Now I got 15 stored. Okay, and that's sort of kind of similar like to a Huffman encoded 15, except that it's not a prefix-free code, but here it's always a pair length and then entry. So in that case, it's different. So all of the following values are encoded a little bit differently. So they're encoded again with this pair length entry, but on top of that, there is something else encoded, and that's called the run length. Okay, so now what's the run length on top of the size and entry, whereas the entry is called amplitude, like this is the kind of the y component is amplitude and the x component is called size. I didn't make this up. So there's one more value there, and that's the run length. So what's the run length? That's simply the number of zeros. So we expect a ton of zeros in here. So the next thing we store are the number of zeros. So in our example here, whoops, I'm gone. In our example here, we have 1 0. So we say 1 0, and then the next non-zero entry is -2, so we find that in the table at row 2, and then the second entry, okay, which is a 1. And if we encode this as zeros and 1 as 2 bits, our bit will be 1. Okay, so next entry is the -1, I think, right away. So we have 0 zeros. We have we choose size 1, and we take the first entry. And this process continues, okay? So in essence, what we do is we do a run length encoding of the zeros, and we encode the rest as entropy, as entropy values, kind of similar to the Huffman code as different variable length numbers. Okay, and that's what we dumped to a file, and here we go. We got our JPEG file. So this is pretty much how JPEG works. If you want to undo the process, you first have to undo this encoding here using that table, which is again part of the standard. So then you do you multiply by Q, which is part of the file. Then you do the inverse DCT. You upsample, if you've downsampled your chroma planes before, you upsample the chroma planes, and voila, you get your not original image back, but close to original image. If you want to get the original image back, simply choose a Q that is full of ones and choose no subsampling. Voila, you got lossless JPEG. Okay, so, but it doesn't work as well as PNG for most of the cases in lossless mode, but it works immensely well in lossy mode. And now what is this high quality, low quality thing from before? Those are simply different Q matrices. Okay, so if you take a program again, such as Photoshop or Affinity Photo or GIMP, it has a ton of these Qs built in. So if you're dragging the slider from high quality, low quality, what you do effectively is you choose from a bunch of Qs that some developer put in there for you. And you don't worry much. You just know that if you drag this to lower quality, it's going to get smaller because of higher values in the Q and higher subsampling and chroma subsampling, and it's going to look worse. Okay, so that's pretty much what JPEG is. This is a final note. We're a little bit over time here, 5 minutes, but I guess it's okay. So just as a final note, on the left you see a JPEG compressed photograph, and on the right you see a photograph of the same size compressed with something called JPEG 2000. So JPEG 2000 is a standard that was developed, well, over 20 years ago, from 1997 to 2000. Hence the name, I guess, around the dawn of the century, everyone wanted to call everything 2000 because it sounded cool. It's now, it sounds pretty dated. But anyways, JPEG 2000 is built on a couple of different ideas. So for instance, it doesn't use DCT, it uses wavelet transform, it uses bigger blocks. So bottom line is JPEG 2000 is pretty much better in most regards. So it has better error correction, supports more formats. However, it's still not used at all. Or not at all is probably exaggerating things, but it's very unpopular. Okay, why is that the case? And it's again one of those historical things. So first of all, it's way more complicated, so it's harder to develop hardware for that, or not, well, harder and in particular more expensive. And while at the same bit rate, it can create much higher quality images, so it's superior in that regard. There's one thing, and that is those really crappy images that you see here only show up in JPEG if you use an extremely low bitrate. If you use a Q matrix with relatively high entries, then you get this pretty bad quality. However, if you choose a pretty small Q, so you don't quantize that much, your JPEG actually generates pretty high quality images. And if you then do a JPEG 2000 image with the same size, it's still going to be better, but the difference is negligible. So JPEG 2000 really flies when you have extremely small files. Now, the truth is, today, hardly anyone is interested in extremely small files. So that's why JPEG 2000 never became popular. And as a matter of fact, JPEG is now superseded by what's called high efficiency video codec or image encoding, HEIC, high efficiency image compression, which is a different concept that still compresses better. So long story short, JPEG 2000 never took off. So no, not much more ado about that one. Okay, but JPEG is still, I guess, for photographs, it's still the #1 format that gets used, and it's particularly the most portable format. So that's JPEG, that was PNG. Those were the popular two compression formats, and that's pretty much it for today. Next week, I want to just talk a little bit about virtual reality as kind of the final topic. So that's going to be Tuesday's topic. And then next Thursday will be the final stream this semester. And just like in visualization, in case you also attended that, I want to give you a chance to ask questions. So you might want to prepare questions already to ask on next Thursday. So you got 45 minutes to ask questions. And if that shouldn't be sufficient, we can add other Q&A sessions later on, but usually from experience, that's fine. Okay, so those were image compressions. And again, we've got a little bit about virtual reality coming up. I just want to look into a few of the technical sides, mostly of VR, and yeah, that's it for today. We don't seem to have any questions at all, no comments at all today. Pretty well, not pretty, entirely quiet chat today, and yeah. So see you again next stream, which is if you watch this live next week, or if you watch the video on demand, just click on the next one. So that's it for today, at least for advanced image synthesis. Stay healthy, get your vaccination, make sure you stay healthy. See you in the next stream. Bye-bye.